Okay, so we're recording right now. So yeah, this talk will be mostly about JAX, and because JAX is the front end for XLA, and most of the users get access to XLA through JAX. You can get access to XLA through PyTorch, but PyTorch doesn't support host offloading, so it's mostly relevant for JAX. So what happens today? JAX sharding decides where the data lives. So right now we have very simple sharding. You have different GPU devices, and accelerator device has a memory attached to the device, and that's basically all. You only decide how do you shard your data across devices. So on CPU, it's easy, it's just host. So the goal is that JAX wants to keep memories and devices separate, compute and data separate concepts. You might have TPU device that has VMM, HBM, and host memory, and CPU device that can access the host memory, or GPU, the same thing on GPU. On NVIDIA GPUs, you can easily access memory that is on device. You can access pinned memory, which is on the host, and GPU driver takes care of moving the data and moving memory pages. And we want to be able to represent that in JAX and XLA and use that mechanism for host offloading. So memory is just a physical memory that is attached to TPU chip, GPU chip, and accelerator might have multiple kinds of memories attached to the device, and it can access the memory with different properties. So latency, mostly it's like how fast the memory is. Okay. And that's how it looks at JAX level. So the sharding, it has a memory kind. So in addition to the mesh and the partitioning spec, you can decide in what memory space your data lives. And it's a string, and we do support device, which in TPU case is HBM. GPU is also memory on device. You can have the pinned memory on the host. You have unpinned memory. So the difference that when you have the pinned memory, you pin the memory pages in the Linux kernel and it doesn't swap them out, and you can do efficient DMAs from the accelerator to the host memory. Unpinned host memory is more expensive because you can't easily do DMAs. You have to go through the staging buffer, and ideally, it's quite cheap to do the pinned memory, so you should prefer pinned memory by default. So what is host offloading? You can offload arrays, your weights parameters or your temporaries to the CPU, to the host that is attached to the accelerator device. And you do that with memories API. There are two kinds of host offloading that we can do in JAX and XLA. You can do memory-only offloading, activations. So if you have some intermediates in the middle of your computation, you can offload them to the host. Another option is offloading parameters and weights. So if your model has hundreds of thousands of parameters and you use them only once, you can keep them on the host and you stream them to device only when you need them and free the memory immediately after the computation. We also can do compute offloading. So you not only keep the data on the host, but you also do computation with that memory on the host, which is attached to the same accelerator device. So previously in JAX, you can do rematerialization policy, had two modes, rematerialize or not. So what happens if you don't have enough memory? You compute some intermediate result on the forward pass, and then you throw away the result, and then you have to recompute the same result on the backward pass for the gradients. So now we also have the option, instead of recomputation, you can offload this data to the host. So you compute some temporary on the forward pass, you move it to the host, basically DMA, copy to the host, and you copy it back to device on the backward pass when you need it. On the JAX side, it's pretty simple change. You have the policy, and you define that you offload from device to the pin host, and that's how the JAX pair looks like. So you have device put, your data starts in TPU HBM on device, and you move it to the pin host memory, and the same for another buffer. And the backward pass, you have some variables that start on the host memory, and then you move them. So they start in the host in the pin host memory, you move them to TPU, to HBM, and you can do computation which runs on the device. And that's how it looks at XLA. This is the HLO for the example. Custom calls as usual. So we don't add HLO that often to XLA because it's very hard, and now it has to go through StableHLO. All the extensions, they're custom calls. So it's annotate device placement custom call that tells that, okay, we have cosine for buffer, and we have to move that buffer to the pinned host memory. And yeah, the same here. And it's another custom call when we move the data back from the pinned host memory to the device memory. And if you extract only the custom calls, these are the most important custom calls. So the device placement, move the data to the host. On the back pass, move the data back. So if you do the movement synchronously, it becomes very slow and expensive and can slow down your XLA program. So what happens at runtime, very late in the end of the compilation pipeline, all these data movement operations, they become asynchronous and they can be overlapped. So in this particular example, you have two start operations. So the copy start argument, this is the buffer that you want to move from device to the host. The result of the copy start operation is the same buffer. So this second buffer is aliased with the argument of the start operation. And this is the real result, buffer of the same shape and size in S5. So S is a memory space and 5 is the host memory space. And you can start another operation. So by aliasing argument with this second result, you basically extend the live range of this argument until the corresponding done operation. So the copy done operation, it takes the tuple of the real result and lifetime extension buffer from the start operation and basically peels this lifetime extension and returns the real result. So this is, at this point, you're allowed to use that buffer for any other computation. And what XLA does is schedule start and done operations in a way to hide computations behind data movement. So on TPU side, we have a cost model, and we roughly know how many cycles, how much time compute will take. So in this particular examples, you don't have anything between starts and done. So, and depending on how do you schedule start and done, you can control your memory pressure. So if you want to minimize the memory, you put done immediately after start, and you free the argument buffer, and then you have the data on the host, and you can use buffer on device. If you can start another option to maximize transfer overlap, you do all the starts and you do all the copy down in the very end. You don't save any memory, but you can overlap your transfers with computation. So XLA is trying to be smart about placing start and done, so it can overlap just enough computation to hide the data transfer latency. So this is how we can do parameter and weight offloading in JAX. So imagine you have optimizer, and optimizer state lives on the host, or input to a program lives on the host. So this is defined by the name sharding. So we have a mesh for devices X, Y axis, and we set the memory kind as a pin host, and we explicitly put this numpy array into the host memory space. And then if you want to use that numpy, that array, JAX array, which is in host memory space on device, we take this argument and put it back in device memory space, memory kind, and this will introduce the copy operation, and this will run on device. And so basically you control when do you want to transfer data to device, and you don't rely on XLA will do the scheduling at compile time, but you have to be very explicit if you want to move the data back to the host, back to the device from the host. And you can do weight offloading inside the scan, so basically the while loop. So while you're running the while loop, you ship the data to device memory space from the host to device, or in other direction. You can, inside the while loop, you can send the data from device to the host memory space. So at runtime, what XLA supports is copy operation. You can copy the full buffer from device to the host, or dynamic slice or dynamic update slice. So you can take the slice of the buffer that lived in one memory space and bring it to another memory space, or you can update the slice. So you can insert the buffer from one memory space into the slice of the buffer that lives in different memory space. So you can take a small buffer and update the big buffer on the host with a dynamic slice offsets or in other direction, which composes really well with scan loops in JAX. So the problem which memories add to JAX is that it becomes ambiguous where computation must run. So historically, computation was always running in the same device where the data is. So remember, sharding defines how do you shard your buffer across CPUs, GPUs. And then when you decide where to run computation, it's very easy. Your inputs are always on the same device. It becomes trickier with memory. So this update function, you might have weights on the host, gradients computed on device, and optimized state is also on the host. And now you have to decide on what device do you want to run the computation. So for that, JAX introduced a computer floating feature. So you can explicitly tell JAX and XLA where the computation must run. So the things that you can do with computer floating, zero offload. It's a nice paper from Microsoft, and they get some nice speed up by keeping all the optimized state on the host and shipping gradients to the host and applying state updates completely on the host. So you free compute sources on your accelerated devices, and you can free a lot of memory. Things like second order optimizers, shampoo optimizers, they rely on QR decomposition, and they have to keep a lot of state for optimizer in memory. So it might be easier to do some linear algebra things on the host if it's not supported on your device. Another thing that you can offload computations that just better suited for CPUs, some graph algorithms, decision trees. If you have any irregular data access, some sparsity, if you have block sparsity, you can write a Palace kernel for TPU, or you can call QSparse. If you have some finite grade sparsity, then probably it is easier to find a library for CPU. Or hash tables. You can't put a hash table on GPU and TPU. Some lookups. If you need to do lookup based on the value computed in the middle of the TPU program, it's probably much faster to ship the data to the host, and you can keep a giant hash table on your host. So you have terabytes of memory on the hosts that are attached to accelerator these days. So this is how compute offloading API looks at JAX level. You have the compute on notation, and you tell JAX that this function G must run on the host, and the function F runs on the device. So by default, JAX G will run computation on the same device, the same device as the PGRT client. So on TPU, it will run also on TPU. For GPU, it will run on GPU. And then you can annotate parts of your JAX computation and to tell JAX that, okay, this thing must be computed on CPU, which is attached to the same GPU device. And this is how it's represented at StableHLO. That's what JAX passes to XLA. You have a call operation, regular function call, and the function call has an attribute which says, okay, run this function on the host. And this is the function, again, StableHLO broadcast multiply pretty standard HLO function. So what is the difference between computer float and IO callbacks? So in JAX, I think for a long time, you can do IO callback and call arbitrary Python code with the buffers. Then I think that computer floating has a tight integration with XLA and TPU compiler. You can do SPMD partitioning. So in this case, function G, if you have a mesh and you want to partition your whole model, it's very easy. SPMD partitioning will look inside the G function and it will do the partitioning for you and will compile the result. So for IO callbacks, it gets slightly trickier. Also, XLA, because it knows what's running inside your computation, it can do more efficient scheduling. Or we can do collectives inside host computation, and XLA can decide to pull collective operation from the host back to the device. For example, if you do collective with parameters of your host computation, it usually doesn't make any sense because you can do collective or gather or reduce on device much faster. So NICO on GPU, ICI reductions on TPU. So it makes sense to pull collectives outside of host computation. So basically, XLA sees the full picture and had a lot of flexibility how to compile things, how to schedule things, how to optimize things. With IO callbacks, it's giant barrier in the middle of your accelerated computation, and TPU is forced to wait for the completion of IO callback. With the host offloading, we can run everything asynchronously, and XLA can efficiently place start and done operations. And in the happy case, you hide all your host computations behind something that runs on device, so you don't waste any cycle on accelerator and you don't waste cycles on CPU. And that's it for the slides, and I have some examples. And I will show. So this is a very simple example of JAX. We have, so this example is running on 4 TPU devices, and we have a grid. We create 2x2 grid and the mesh, data and model. And this is the sharding. So this is device sharding. It tells JAX that we partition the data over this mesh, over this dimension. And this is the same sharding. So the same partitioning spec, but we tell JAX that, okay, this data must live in the picked memory space. We have some NumPy array, and I just put it on the device sharding. And this simple function. So function F will run on the TPU, and function G will run on the CPU attached to the same device.
So you explicitly annotate that G is going to run compute on the host, but you do not annotate that the memory should be on the host. It'll implicitly copy that from device to host.
So yes, let's take a look at the function F before optimization. So we have a call. So no memory spaces, no layouts, very simple HLO. So we have a call instruction. We apply this function, and we want to apply this function on the host. And the function on the host, G, one operation, and bunch of metadata. So what happens that function F after optimization, we have the call start instruction, async start, and we run this async operation on the host execution thread, and we call async computation, bunch of metadata, and the input to this operation is this buffer. So first of all, we have 8x2 array. This is after Steam departitioning. So the input size is 4x2 because it got automatically partitioned. And we have this tiling, which is TPU tiling. And we pass these TPU buffers to the host computation function, and we get back another TPU buffer. And this is the function that will run on the host. You see it has linear memory layout because XLA CPU expects a raw major layout for all parameters. And it also was automatically sharded. It's 4x2, one operation. And we have the second model. So this one, model one, this is the thing that runs on the TPU device. And this is thing that gets compiled by XLA CPU. So we introduce a fake parameter. So because XLA TPU owns the memory for results and XLA TPU owns the memory for parameters, and XLA CPU must become a destination passing style computation. So by default, XLA will allocate result buffer for you, but we already have a result buffer, and we want to force XLA to write into that buffer. So we do that with input-output aliasing. We have this fake parameter, and we tell XLA that the first result must be returned into that buffer. And yeah, it's also partitioned 4x2. It's also after Steam departitioning. And for the host offloading, we use regular XLA CPU. And this is what we get after compilation. Yeah, it's pretty boring example. For example, I will add second operation. Because it's a regular XLA CPU, we have fusion. So because we can fuse two operations into one kernel, we have sign fusion, fusion parameter. So we don't invent really anything new for the host offloading compilation. We just take XLA CPU, take XLA TPU, and the host offloading takes care of moving the data between accelerated device to the host, doing layout conversions, invoking XLA CPU, and moving data back. And if the data is already on the host, it doesn't have to do anything. If the data is in GPU, it has to do DMA. If the result is expected to be on the device, it will also do DMA. If result will be in place update of your weight buffer that lives on the host, no DMAs will happen. You just update the buffer owned by your runtime. A more interesting example that you can extend your XLA checks program with XLA FFI. So imagine you want to run something on your host, so IO callback. If you want to do IO callback and use Python, as I mentioned, it must not be efficient. But in XLA CPU, what you can do an FFI handler, basically a custom call. I have my custom call defined for this example. It's very simple custom call. It just adds one to, you have input rank to buffer of floats, and we have result also rank to buffer of floats, and we just add one to every input element and write to the output. And that's how I can register the C++ function with an XLA runtime. I just define a handler. This is my input buffer specification. This is the result. And I register the C++ function as host offloading custom edition name on the host platform. And then I can use JAX. So JAX has an FFI JAX extend. It's a namespace for a bunch of JAX extensions, and FFI is one of them. And there's documentation on the JAX website. So again, we have the same grid, the same mesh, same shardings. And in this particular example, I'm using custom partitioning for my custom call, because by default, if you don't define custom partitioning, what XLA will do, it will gather the data for all partitions and call your custom call with a full buffer, but that's not what we want to see in the example. I want JAX and XLA to partition my computation so that I get the per replica array as an input to my custom call. So you can find my documentation for the custom partitioning on the JAX website, but basically this is the main function. You define how do you partition your function for that particular argument, and what we do, we just insert an FFI call for my custom C++ function, and I expect exactly the same shape and type of the result. And I'm inferring sharding from the operands and results. And this is my custom addition function. And I defined the partitioning spec for my custom addition function. It's pretty long and complicated. I have a much shorter version of that below. But this is the same. So inside the host offload computation, I'm calling my custom C++ function, and I want to call it from my computation that runs on TPU device. So this is how the function looks before SPIM partitioning. You see it has 8x2 shape and has a custom call, 8x2 custom call that I call custom SPIM partitioning. It hides the real custom call behind this attribute. And this is my TPU computation. Again, I have a call which runs on the host platform, and we'll call this function. After optimization, this is my SPIMD partition models. I have the real custom call. So custom call, my host offloading custom edition. The important thing that it got automatically partitioned. So it is called with 4x2 array. And I have the same async computation that orchestrates asynchronous execution of my host offloading computation. And I have the call start and call done. and inside my, so this is the CPU part. Very simple, just a custom call that calls my custom addition. And I can see in the logs that I should be able to see it somewhere. Okay, I can't find the logs, but you can trust me that custom call was called somewhere. So custom partitioning is pretty scary API and it's very hard to get it right. So in JAX, you can have the shard map, and shard map automatically works with FFI calls, and it's easier. So basically, you have to write your function per shard, and you don't need to define custom partitioning. See exactly the same, my custom addition function that runs on the host device, and I use an FFI call for my C++ function, and I plug it into my computation running on device. And I use a shard map on this mesh with this partition spec, and it automatically will distribute this function across all the devices. So I should have it. So this is another HLO after optimization. Again, you can see it's shape 4x2, which means that we're running my custom call with a proper array corresponding to the partition, and the same call start, call done. And if you don't do it correctly, you will get a bunch of collectives on the host side. And collectives on the host side, they're typically more slower than collectives on the device side. So ideally, you should be able to run your host computations without any collectives, because collectives will massively slow down everything. And again, this is your call computation that runs on the host. Again, with a simple custom call. That's all examples I have. So the main idea that host offloading allows you to combine XLA CPU with XLA TPU and mix them together, and you can seamlessly invoke any XLA-HLO JAX function from your accelerator. So right now it's implemented only on TPU. We think about implementing that on GPU. It will take some time. So it was designed, so all the compiler passes, all the runtime integration, it's very backend agnostic. So there are some layout conversions. There is no layout on GPU. Everything is row major, code major, maybe permutation of dimensions. We don't use tiling on GPU. At least I don't know that tiling is used for anything important. So there are some bits that are very TPU specific, but other than that, it is a very regular XLA CPU and XLA GPU, TPU, and we have the layer that knows how to move the data back and forth, compiler passes that can deal with calls with annotations. Scheduling is pretty standard. You have the copy start, async custom call. So everything should work out of the box. The problem that on GPUs you have few memory, and that's why it's high priority for CPU to make computer offloading work. On GPU, memory is usually available, and NVIDIA in general is not interested on running compute on the host. So I think NVIDIA thinks that all the flops must happen on GPU. We don't think that way on the TPU land. I think it's fine. Some flops are better to run CPU. So depending on the interest on the real world use cases, we plan to make it available on GPUs. It might be Q4, maybe Q1, maybe Q2, depends on if there's interest. AMD, if your AMD wants to see computer offloading and mix and match AMD CPUs plus GPUs, we can try to make it sooner, because overall it was designed to be composable with all backends. It just happened to be developed inside TPU backend because it was faster, but it doesn't have anything that is secret.
So let me ask you something there. What is the communication link between the host memory and the TPU? PCIe. So PCIe is going to be inherently very slow compared to any HBM link.
Yes.
Right. how does the compiler take care of that in terms of, because you have generic computation being scheduled on the host, and then it is conceivable that there is some data dependency between when that result becomes available and when the rest of the TPU, GPU pipeline can.
For example, for optimizer state offloading, there's nothing on device that waits for the results. Only the next step waits for the results. So if you have your gradient, computer gradient on device, you can ship to the host, you apply updates to your optimizer state, and only the next step has to transfer the data back to device. And usually you have enough time between the steps to hide the latency. Also, because you have copy start and copy done, what you can do, you can, if you have multiple gradients for different weights, for different parameters, you can immediately ship them to the host immediately when they become available. And in the very end of your training step, you have the last gradient that you have to ship to device. And then you can immediately start the computation on the host and go on. And on the next step, you have to, again, you don't have to ship all the weights back immediately to device. You have to ship only the first one to start doing something useful. And then by the time you have to ship the second one, hopefully it's available. So if you do scheduling right, and if you do your computation right, you should be able to hide most of the latency. And I think that Zero paper, they also discuss that. So how they do asynchronous execution to be able to transfer the data ahead of time and transfer results separately. So we don't have to wait for all results to be available to start doing something useful.
And how does the cost model to compute the transfer time work? Because if you're transferring weights from the host for the first iteration to come out, right, you're basically essentially computing the bandwidth of the PCIe to determine how long it's going to take for this tensor to be available for the next operation.
Yeah, I mean, assuming you don't have anything else consuming your PCIe, you should be able to, XLA, can understand how many things are in flight in the PCIe and understand roughly how much time is going to be spent on the transfer. And then it knows how far apart to put the start and the done so that there's enough compute happening in between over the duration of that transfer.
Okay. Yeah, it's interesting. We can definitely.
For the compute offloading, you don't actually have explicit copy in the graph, right?
Yeah, you can call the host computation with the device buffer,
Right.
and the runtime will take care of the transfers. You can call it with the host buffer, so you can explicitly move the data ahead of time and call the host buffer. So the runtime can support, host buffer, pin member, and pin memory. Host buffer can be in device layout. It can be in raw major layout. It can take device buffer in device layout. It can take device buffer in linear layout. Basically, runtime, like the integration between TPU and host offloading executable, it takes care of moving the data in changing layouts, so we can call XLA CPU.
Yeah, so if we were to estimate the latency for this, offloaded compute, the estimator has to take into this, implicit copy configuration. Okay.
Yes.
Is the implementation dependent on sharding?
No. So from the XLA perspective, we get SPIMD partitioned HLO, and we get the replica ID, partition ID, but we don't really know anything about sharding. So we have XLA CPU executable attached, or multiple XLA CPU executables attached to a single XLA CPU executable, and you call them concurrently for different partitions on the same host. So they all run in parallel on different threads, and they might communicate to each other through collectives, but they themselves don't really know, are they the part of some bigger sharding, bigger group.
So is there a global dispatcher for all the computes to different devices? Where does the cogent happen? IR load?
I think the same PGRT level does. So for GPU, if you run multiple replicas on the host, so PGRT will call XLA concurrently inside the thread pool, and it will be exactly the same XLA executable called by PGRT in different threads.
Okay.
And you call them concurrently, but you just change the device ordinal and stream executor. So in GPU case, you just call the same XLA executable with different instances of stream executor. In TPU, something similar. You have a single TPU executable, you call it on multiple threads, and inside your execute params, you tell, okay, this is replica 1, replica 2, and so on.
Is there any performance analysis or comparison with offloading feature versus all-in-one hardware like GPU or TPU?
We have some benchmarks. So I think like Gemini, like 15, 20, 25% improvement from memory only offloading. From computer offloading, I don't think that we have results. I think it's very new. It's done. It's not yet done. It's very functional.
But is there like a performance difference between when you do memory offloading versus when you don't? Or
We worried mostly about memory savings. So
Okay.
if you can keep optimized state on the host, you need fewer chips. Your collections become faster because you need fewer chips. And if you're smart enough about scattering, you can hide all the latency and all the compute on the host behind communication and other computation running on device.
and your results support that the performance stays the same essentially?
Not yet, but that's the goal.
Okay.
I think right now, maybe 5-10% performance degradation. It depends how lucky you are. It depends what you're running on the host. If you're running some giant matmos on the host, okay, you'll be slower. If you're running something simple like RMS prop Adam on the host, you should be able to hide it with scheduling and optimizations. And we keep working on performance optimizations on the XLA CPU side. So XLA CPU can be faster and XLA CPU can keep up with TPU devices. So the difference in terms of flops is huge. But again, if you have hash table, you can't put hash table on GPU, TPU. If you have something that requires random memory access and you have it implemented in CPU, and you don't need to transfer giant buffers through PCIe, because this is basically the cost of microseconds. It's microseconds to call computation from device, and the same like from GPU and TPU. It's pretty cheap. If you don't need to transfer a lot of data, you can very efficiently hide the latency.
So it's when you refer to hash table lookups, are you talking about the key value cache optimizations?
Yeah, we have super cool projects. They're super secret. I'm not allowed to talk about them, but we put on the host computations that just don't work well on TPU or GPU.
Okay.
And you have a lot of memory on the host. It's hundreds of gigabytes easier.
So for machines with multiple CPUs, is there a way to specify which CPU the closest one to offload?
Not right now, but that's the goal. So right now, PGRT and XLR CPU, they don't know anything about the numerals.
Right.
The long-term goal that you have a TPU executable and right now, it's implemented the way that TPU PGRT client has an instance of CPU PGRT client, and TPU PGRT uses CPU PGRT to run host loading executables. We plan that single TPU PGRT client should own multiple PGRT CPU clients for different numerals. So we have to pin the threads because it's always you must transfer the data to the same num node, and you have to scale computation with the same num node. I think though today at Google internally, I think that works magically out of the box because how scheduling works. So we get it for free. So that's why we didn't implement it. But in open source, yes, I think if we will do that for GPU, we'll have to make it NUM aware.
Yeah.
We always run everything on a single NUM node, and the cluster scheduling, it scales jobs and pins everything to a single NUM node. So we automatically get NUM locality for free. Right?
Just curious, so which use cases have benefited most from compute offloading to the CPU?
The super secret ones that I can discuss.
Okay.
Do you have?
And also, you're not sorry, one more question. You're not restricted to use compute offloading for FFI custom calls, right?
Anything. You can put anything. Any JAX function, anything.
Okay.
But we found it useful that things that are representable as HLO, you probably better running it on accelerated device. If things is not representable by HLO, you probably write as a custom call, and then you probably should use FFI, and that's where you can extract most of the benefits from CPU, like hash tables. We don't have hash tables in HLO, but if you want to keep cache on the host, hash tables, some fancy lookups, you'll probably end up writing custom C++, and you have to plug it into XLA and JAX.
Okay.
You mentioned the generic nature. Here it's CPU offloading for compute. Is the interface generic enough that we could say use a GPU as an offloading device? If you're working with an accelerator, you want to offload to GPU or CPU, like essentially.
Right now, it's always your accelerator, TPU, GPU, and the host. So the main device is always accelerator, and device that used for offloading is the host that is attached to accelerator. And we don't have hosts with TPUs and GPUs. So it's always one particular kind of accelerator attached to the host.
Okay.
So yeah, conceptually, if you have a host with GPU and something else, that can work. You just need to introduce another compute-on device type.
Okay, so the API could do it.
Yeah.
Yeah. Okay.
It's basically annotation. So if you have your annotation, please think. So instead of host, it will be something else. And if you have basically the idea that you have two PGRT clients and they can talk to each other and send data between each other. So you have PGRT client for GPU and PGRT client for something else.
Yeah.
Yes, conceptually, host offloading should be able to connect them together. Maybe we should rename it from host offloading to something else then.
Are there any tutorials out there which describe any examples that show the usage of compute offloading?
Everything is public on JAX memories test. I don't think that we have any documentation on the JAX website. That's something we'll work on. I think right now it stays mostly private because it's not supported on GPU. And JAX team loves to have full backend support for all the features. It's nice to have feature parity. So I think once we'll get to GPU, host offloading and GPUs, we should have better documentation on the JAX. But if you open this memories test, it has a lot of examples for compute on. Yeah.
Okay, thank you.
A bunch of examples of offloading different things and mixing and matching memories and compute.
I think for GPU, the copies are added like in Remat after fusions. Do you think it's beneficial to fuse these copies or not?
Well, if copy is a kernel, then yes. If copy is a CUDA mem copy, then it doesn't really matter.
Right.
Yeah, it depends on CUDA implementation. If you schedule multiple memory copies one after another, how well CUDA will execute it.
Yeah, I guess if you have a giant copy with multiple transfers, maybe you will schedule that just single copy. So that's
Maybe there are cases where there's other stuff going on the host where we want to break it up into multiple distinct copies so we can get in something that's higher priority rather than hog.
right. Yeah, that makes sense.
That's a good point. Let's say there's other workload or some other work running on the host CPU, right? That would essentially disrupt the estimation of the schedule that XLA thought up, right? How do you deal with that?
Don't.
Okay, just hoping it'll play nice.
We hope that nothing else is running.
Okay.
Because, for example, for optimizer offloading, it might be very expensive computationally. So yeah, we hope nothing else is running because we will use all of the CPUs.
Okay.
Because if you have 8 devices attached to the host, and if you have hundreds of gigabytes of data, optimized state, XLA will run concurrently, everything is multi-threaded, so we easily can use all the physical cores available on the host. Yeah. So we do see noisy neighbors is a problem. If you have something else running on the host, you'll see huge performance regressions.
Okay. And on the TPU, what kind of memory is attached to the host? Is it the same HBM or is it a different kind of?
The host like regular memory on a regular memory.
DDR.
I think for devices at GPU, you can specify priorities where you want to run this. But is this same thing for if you want to run host kernels and specify priority?
Yes, I think you can specify priority on thread in a Linux kernel. Thread pool. We have an option to support priority in thread pool, so yes, you can. Okay. It was implemented, but it's not really used right now. But yes, conceptually, we can add priorities to thread pool that is used by StableHLO. And we have pretty dynamic scheduling, so you can optimize for time to first result. So right now it's pretty simple. Right now we run everything concurrently, randomly on random cores, and we hope that the Linux kernel will do the okay thing. Like mostly local data. We hope the data will stay mostly in L2L3. But yes, we can improve that a lot. Like normal local priorities, better scheduling. But yeah, so right now we have the very basic mechanism to plug an XLA CPU into your accelerator program. Yeah. And we work on XLA CPU to make it faster, more efficient, better use the resources available on the host, and so on. Yeah. I think that's all. No questions online? I'll stop the recording.